on programming network policies by examples, and also some of our experiences in carrying out controlled user studies in programming languages research. So we are all here today to learn about programming languages in SDN, and I think the number of people in the audience is really testament to how vibrant the field is. And so on one hand, you have general purpose programming languages. They are more traditional C, C++, Python, and so on. And on the other hand, you have this proliferation of different types of domain-specific languages. But what's missing here is SDN programming for non-programmers. And why is that an important thing to do? As it turns out, a lot of the consumers of SDN or programmable networking technology are really the network operators, where they may be very well versed in configuring their networks, may not necessarily have the type of background to actually program them in software. And we see a lot of that in, for example, big telcos sending their network operators, which have decades of experiences in configuring networks, to actually go for programming and software programming type of lessons. Now, to validate this, my former PhD student, Yifei Yuan, and I, what we did was we carried out an interview of 101 network operators, architects, and software engineers from across the spectrum and router vendors to try to understand the need for programmability. This was actually done in the context of a NSF Innovation Corps program, which is a really wonderful program that I'm happy to talk about offline. But one of the things we learned about is there is a strong need for programming skills among network operators. There's a need to do frequent configuration changes, and a lot of that should be automated. But one of the biggest impediment is the lack of programming expertise. And as part of our study, we also looked at kind of the need for programming skills on whether it's a good to have versus a strong and a must need to have. And we found that there's actually a large fraction which consider this to be absolutely critical. So in the rest of the talk, I'm going to give an overview of NetEgg, which is a paradigm that allows you to program by examples. This was work that was presented in 2015 in CONEX. So I'm going to give an overview, but the second part of the talk, which is also what I want to focus on, is our experiences in carrying out our controlled user studies. All right, so what is NetEgg? So NetEgg is a programming platform that allows you to program by example, right? So for example, if you look at a traditional SDN kind of environment, somebody would go and write the actual policies. But in the context of NetEgg, what we have is instead the operator on the bottom left, they will specify scenarios, which are essentially input-output examples that describes the policy of interest. And this is then fed into a synthesizer. It is a program synthesis tool that will generate the policy, which is then run on a general purpose interpreter that implements the policies themselves. Now, NetEgg is meant to be an iterative process. What it means is that the operator will write some input-output examples, compile and run that, and then based on the behavior that he or she observed in the actual execution of the policy, then what you do is you come up with counter examples that, for example, shows violation of invariance, and then they'll incrementally fix the input-output examples and then feed that back to the synthesizer again. All right, so to illustrate this programming by example paradigm, I'm going to show you a simple example of a learning switch. We have done actually a broad spectrum of examples. And the kind of a mental model that we use here is essentially timing diagrams that we see in any undergraduate networking class, right? So for example, if you look at this picture on the right, you can see that in a learning switch example, for a given packet, right, which is coming on a particular port P1, and it came from a source HA and a destination HB. The first time, in the absence of any knowledge, you're going to simply flood the packet. But what you have done in this case is to build up knowledge for the next time you see a packet that is designated for HA, right, host A. And you know that that must have came from port P1. So rather than do a flood, you can simply forward that to P1, right? And the third one kind of completes the scenario, which says that now that you see a packet of that form, the next time you see a packet that's going to host HC, you can simply forward that to P2. Now, one of the things to note here is that P1, HA, and HP, they are all variables, right? So you're not really describing some constant specific behavior, but this is kind of a more general way of capturing the behavior of your protocol. Now, in a lot of real-world examples we look at, it turns out you need more than one scenario, sometimes 2, sometimes up to 5, in order to capture the policy of interest. Now, based on these examples, what our tool will do is then automatically synthesize the actual policies themselves. And the kind of policies we want to focus on are those that are stateful in nature, right? Essentially, you have some state and also a couple of cases. So for example, in the learning switch case, the state would essentially be the mapping from host to pods. And you have 2 example policies, right? In the first case, if the destination is not known, then you flood the packet, but you remember where it came from. And in the second case, if you already know, then you could simply forward that along. So here you can look at an example of the execution model. On the left, you see the state table, which is automatically synthesized, right? This is actually not something you have to hard code. It shows, for example, in this case, the mapping from MAC address to specific port numbers. And the policy table on the right, which shows kind of a generic form of doing matching. So if you have a match, right, you apply a particular test, and based on the test to see whether you have remembered that MAC address in your state table. And based on that, if it's not there, the action would be to flood, but then you update the state table. On the other hand, you simply forward that along, but also update the state table. Now, this particular execution model is very general purpose, and it turns out to also have been explored in prior work. It's very fast. It's expressed different types of dynamic policies. And what we have done in this NetEgg tool is essentially to program your examples and automatically synthesize this policy table, right? So what you see on the right-hand side is something you would do at compile time, but the state table is generated at runtime. All right, so the NetEgg tool takes as example different scenarios and then automatically generate the policy table itself. And one of the goals of doing this is to make sure that we can come up with a synthesis algorithm that gives us a couple of important properties. The first, of course, is that it has to be correct. In other words, the policy that you generate has to be consistent with the examples that you give. But at the same time, it also has to be minimal. In other words, if you can generate 3 entries in your policy tables that faithfully implement your scenario, right, you shouldn't have to have 4 or 5 entries. So I won't go into the details of the synthesis algorithm, but it turns out that this builds upon a number of wonderful work done in formal methods on program synthesis. One of the ideas that we looked at that worked really well is this notion of greedy search that will explore different examples. And then in such cases, we also do backtracking with pruning if we hit upon a particular scenario of configuration in the policy table that no longer is consistent with your scenario. All right, so the other thing that happens is at runtime, right, given the policy that you look at, you see on the right side, you can actually then dynamically push down actual configurations to the switches. And in this case, this is done by looking at rules, right? And if they no longer update the switch tables on the switch itself, right, then you can push down some of these changes, right? So for example, if you learned in the past that a destination MAC address of A should be forwarded to port 2, then this could be pushed down to the switches at runtime. All right, so in our earlier evaluation, we focus on a couple of things, right? And this is sort of the one standard way to evaluate the effectiveness of programming languages, right? Which is we want to figure out how expressive it is, right? what is the breadth of examples or the type of applications in which this is particularly suited for? Is it intuitive, right? And it turns out the second one is really hard to quantify, right? Unless you have, for example, some actual user experiences, which I'll get to in a minute. The third is conciseness, and this is something that could be quantified relatively easily looking at lines of code. But as we know, it may not be the best proxy for productivity. And the last one is efficiency. And that is measured in terms of standard metrics such as latency and throughput. And the fourth one, as it turns out, is something we have a lot of experiences with. All right, so one of the things that we did was to look at a breadth of use cases. We look at across the spectrum different policies that people have come up with, but focusing on stateful policies. And the interesting thing that we found is that in large part, the use cases that we looked at could be expressed in relatively small number of scenarios and also a small number of events. And this also translate into relatively low synthesis time, right? So in the kind of a most extreme case, we have an example that requires 402 milliseconds, but given that this is done at compile time, it's relatively kind of doable and feasible. Now, in terms of code sizes, you can see that, so one of the things we did was to compare NetEgg against other approaches, and we found that this results in orders of magnitude reduction in code sizes, or fairly large. But at the time of Conex 2015, we were somewhat dissatisfied with our own results in the sense that we did not feel that lines of code was necessarily the best way to evaluate a programming language, but turns out to be the most objective and easily quantifiable metric that people have looked at, including us. So we also looked at performance and comparing NetEgg with POX, and we see that in large part we were able to get close to the actual implementation in POX doing the same functionality, right? And in terms of end-to-end performance, we did a actual experiment using HTTP server on a factory topology. So I won't go into too much details here, but one of the main takeaways that in terms of the actual throughput, we were able to also approximate the performance of POX. All right, so NetEgg is a tool. It's a graphical tool that's available. We plan to release this as open source. And I think one of the really cool things is that it's also usable in the classroom setting, right? So anytime you teach any undergraduate networking class and you have introduced these kind of timing sequence diagrams, it turns out to be a very intuitive way for students to learn about policies and protocols as well. All right, so the second part of the talk, which is kind of one of the things I want to get to today, is on controlled user studies, right? Which is a kind of a way for you to understand or quantify the effectiveness of a programming language. And we tried to carry out this study in 2016 and 17. And part of that was talking to social scientists to understand how they do user studies, right? And to see if how much of that we could actually bring into the programming languages domain, right? So for example, in the context of any programming language, this is in networking or outside of networking, what we want to do is to test the hypothesis. Are programmers more productive in programming language X compared to programming language Y for solving problems of type Z, right? And in a controlled user study, what you would like to do is to keep all the factors as constant as possible. In other words, the only thing you will want to change is the programming language itself. So for example, the people in the study should have similar types of background, and you should only solve the problem once. In other words, you divide your participants into two groups, one that will solve it using X and one that will solve using Y, with a similar background. And the whole idea of not allowing them to solve the same problem twice is that clearly the second time they do it, it's going to be easier even in a different kind of programming language. And we also would like to do it in a controlled setting under a watch where we could actually time users and heavily instrument the software environment. In other words, not only we want to look at their final output, but also to understand their behavior as they went through mistakes and iterate over their design. right? And here's a picture actually of Ife carrying out the controlled study. Not surprisingly, this requires IRB approval. We require the students to sit in for 3 hours and for a nominal sum of money and pizzas, which frankly wasn't the main motivation. The way we kind of sold it to students was that this is a chance for you to learn about SDN as well, and we actually got quite a few. Go ahead. IRB? Oh, that's a approval process to do human subject research, right? I don't actually remember what it stands for. Maybe one of you would, but basically anytime. Thank you. So anytime you want to do a human study, you have to go through this process, right? And it's a fairly kind of lengthy process sometimes. And if it actually, in a way, gets into the way of publishing papers too, and I'll talk a little bit about that as well. All right. So why are we interested to do user study? And one of the things I would argue is that the best time to do it is early in the programming language design phase, right? Because what you want to do is to also be able to identify the mental model of your target audience. So for example, when we talk to network operators, we see that they don't talk that much in terms of pseudocode, but they love to draw diagrams. They love to draw messages flowing back and forth. And this is really the mental model that we're trying to capture here. Now, note that this is complementary to some of the other approaches we have seen, right? So the most common approach is releasing this as open source and hope for the best, right? And if your tool turns out to be great, then you're going to get large adoption. And the other approach that we have done in the earlier work on declarative networking, and this is also done in the Kinetic project where they did it in an online kind of learning fashion, was to do it in a large classroom setting. And I would argue the two approaches are complementary in the sense that the second one allows you to get a much larger pool of users, but the first allows you to actually observe your target audience or the early participants. And one thing that I came to realize having done both is that the first is useful in the early stages, while the second is more useful when your project is in a more mature state. All right, so in the context of the user study, some of the things we want to find out is, can NetEgg reduce the error rate of programming SDN policies? Can it reduce user productivity? And the third one is, how are users actually interacting with NetEgg? So to do this user study, we compared NetEgg versus POX, right? And the type of users that we look at, we wanted to keep consistent. So we enlisted master students, doctoral students at Penn. In the ideal case, we would love to get actual operators, but in the absence of that, this is the best proxy we could find. And we do require the participants to have at least taken a networking or distributed systems class, but they need not know anything about SDN. And we actually did this study a couple of times, right? The first few times were actually to get our tool into a state where it was able to kind of be of what we call production quality, in the sense that we want to factor out any sort of loss in productivity that's tied to the tool stability, but more tied to the programming environment. But eventually, in the final stages, we looked at kind of the actual study itself, where we had 15 users in NetEgg and 9 in POX. Obviously, the ones in POX needs to know Python, and there's no such requirement in the NetEgg group. Now, the specific assignment we gave them, right, we didn't want to give them a simple learning switch, but something that was a little bit more involved. So we looked at a firewall plus, which is generic firewall policies with a little bit more twists and turns. So it becomes a case where they actually have to think a little bit harder and before they could come up with a solution. And here are some of our results comparing POX and NetEgg. One of the things that we found is that the NetEgg approach, people were actually able to get the correct answer all the time, whereas there were some mistakes in the POX approach. Keeping in mind, it was easy to look at examples, right? And when you actually see the examples do not work, there was an easy way to kind of feedback the counterexample back to the tool, right? So it makes it very easy for them to kind of tweak the examples to try again. The programming time turns out to be about 50% reduction compared to POX. And in the last case, we wanted to look at how users interact. To do that, what we did was we heavily instrumented the programming language environment, so we were able to capture scenarios that they added, scenarios that they deleted, and all the tweaks that they kind of make along the way. And we were able to identify 3 interaction patterns, right? One is the smooth interaction, one is the back and forth interaction, and the other is what we call the stuck interaction. Right, so in the smooth interaction, this is the best case scenario, right? People come in and they get out in 20 minutes, right? This is the case where they were able to monotonically add new scenarios and get the correct answer really quickly, right? And certainly we see students falling in that category. The second is the back and forth interaction. This is cases where they try some scenarios, it didn't quite work, right? It didn't pass all our regression tests. They look at the counterexamples and then they say, aha, actually, I need to go change this thing. I need to drop this scenario, right? And then they go through some kind of back and forth process before they eventually get the correct answer. And the third one is the undesirable one. This is the stuck interaction. And this is actually a kind of a problem that you have, whatever programming language to use, right? And in this case, the participant went down a rabbit hole, right? They were wrong. But rather than take a step back, they kept kind of digging a hole deeper and deeper and making the scenarios more and more complicated, and take a while for them to get out of that. Now, statistically across the board, we see that a large fraction of them fall in the smooth interaction case. There was some back and forth, but we also see an example of that getting stuck. And not surprisingly, the ones that were stuck will end up taking the most amount of time. All right, so in terms of user feedback, we kind of gathered a number of feedback. Some of the positive ones were that the tool was easy to use, and it was very clear how to use that. But we also had some participants that got a bit confused, particularly, I think, in any sort of domain-specific approach. It's sometimes easy to kind of get confused over some high-level abstraction. And in this case, it was actually this definition of variables, which was something we didn't quite anticipate. All right, some of the takeaways that we had in this user study, we found that to be extremely educational and useful for us, right, as people who work on new programming languages design. As I mentioned earlier, participants found it intuitive, but also had some confusion. But that actually helped us inform our design so that we could kind of improve our tool. Now, one of the shortcomings of such a controlled user study, which is why I think this could be combined with a much bigger kind of study in the wild, is that we have a finite number of participants. And in fact, if you do not get your study right the first time, unlike your experiment where you could go back and rerun it tomorrow, you couldn't go back to the same person and say, can you redo this again? Because yesterday I forgot to do something, right? It just didn't work. And in fact, we had a painful experience, right? We forgot to capture some questions in the Q&A on some of the users' background, and we had to invalidate a pool of users as a result. And one of the takeaways we had was that in order for this study to be effective, given that you can only have somebody participate once, is to really get the study right early on. One of the missing elements that we had was this lack of longitudinal analysis, which is what happens when somebody uses the tool again and again. So for example, a particular programming language could be really hard to learn the first time, but once you get it, the next 10 programs are easy to write, right? So that unfortunately was a missing piece. All right, so I'm going to kind of summarize in kind of this talk. I presented to you NetEgg, which is a way for you to use scenarios or examples to program SDN. And we kind of operate in a different design space. We want to target people who don't necessarily know how to program, but who may be experts in managing networks, to try to see if we could come up with abstractions for them to be just as effective they are in implementing their policies without having prior knowledge in a particular language. And our user study does show evidence of improved productivity. Now, I think this is an approach that's likely to work across different domains in networking, and I just want to briefly mention a few. The first is measurements, which was presented in Jen's talk as well as Nick's. And measurement is a really interesting example because this is one where you could have users express patterns as examples, and we see some success of that in the program synthesis literature, right? So people have used, for example, to do data cleaning in Excel spreadsheets. We've seen work done at Microsoft, where instead of writing the logic for the cleaning, you provide examples on what the initial data looks like and what the clean data looks like, and your synthesis tool will then learn the pattern, right? I think measurements has a lot of that sort of phenomenon where I think this could really apply. Likewise, in data plane processing and also in recognizing attack patterns in security, I think these are all good domains to look at this programming by examples approach. So with that, I'm happy to take any questions. Well, anyone, please go ahead.
So I thought this is really interesting. Going back, and I like the fact that you had a real evaluation of real users. That's always really great to see. But your target audience seems to be network operators, people who work at network operators. And so I guess my question for you is how would you do an evaluation of the effectiveness of a tool like this for them? Because or is the implication that even if you teach them programming, they're better off using a tool like this? But I guess how would this change if you were doing an evaluation with your actual target audience?
Great. So so let me repeat. The question is on how would this tool change if we were to target network operators? And I think you did point out sort of one kind of limitation of our user study was that we looked at students who were not necessarily network operators. And we saw that in a couple of different social science work where people do studies on, say, mechanical Turk. There was also this, because you couldn't get hold of obviously it was a lot more expensive for us to go after operators, but there are other proxies of that. So back to your question on how we would do it differently, I think that as the tool matures, right, one option is that you could release the code, put it up as a service, and then have operators actually try them out. But ideally, you want to do that early in the design process, right? There's always this question of, could you get your customer early in the design process enough, right? So obviously, we couldn't get them from day one, but could we get them, say, when the tool is at some level of maturity? And to try that on some of their use cases. Right. Yeah. Go ahead.
I have a question about your target. So configuring network is not so complicated. What's really complicated is that you can state changes, whether new policy configure has broken old one, and doing this network-wide. Have you looked into ability of people to understand the impact of the policy rather than just blocking particular part?
Also, if I understand the question correctly, is on the configuring policies where there were kind of state changes.
You always change state
Yep.
to configure something, right? But it's easy to configure, it's difficult to understand what it does to the rest.
Okay, so kind of side effects on other things. This is actually where, so first of all, this particular NetEgg tool is designed for stateful policies because as you write your timing diagrams or sequences, it's kind of accumulating state as you go, right? So the behavior may change based on the earlier kind of sequence of interactions that happen. But the other point about side effects, this is actually where it becomes useful to look at counterexamples, right? Because you could always study your policy in isolation, right? But how it interacts with others, you may not know how that would interact unless you actually run it. right? So, and one way you could actually kind of go about using a tool like this is an iterative design process, right? Which is you observe something goes wrong, and then you go back and try to use this as counterexamples to change. In fact, when we started out this project, we had a slightly different goal, was that we wanted to say prove correct all the way, right? Which is kind of the goal of most domain-specific languages, was that you write it in a domain-specific language and then you prove that it meets a particular property, which was actually also some of the things we looked at in our early work on declarative networking. But one thing that we found is for a tool of this form where you're programming by examples, the sweet spot isn't so much in proving all the way to meet some property, but rather to look at how it interacts in the wild, in when you actually deploy it. Because you could actually use the execution trace and the kind of bad behavior directly in kind of tweaking your policy again.
Okay, so sorry, we are running a bit short on time, so I'd like to set up the next
Sure.
talk.
All right, thanks.